All right, class. Let's go with it. Let's begin. That was very fast. All right, class. So let's see. Today is Monday. Welcome to Monday. We'll see. We have something called pictures or something happening soon. Is that right?
Yes,
on Wednesday. Pictures on Wednesday.
I'm going to forget.
So remind Camille so she won't forget. Let's see. Beyond that, what else is there? I think that's it. Oh, that's it. So I graded your exams. I think I've graded your rest of your chapter or Appendix A homework. I think I've got that done. So then let's see. I'm going to hand back your test today, and here's the way it works. 4 is you got full credit for the problem. We're good. 3 is there's a minor error. 2 is there's a good computational error. That's an issue. 1 is I had no clue what you're trying to say. You went this direction. And then 0 is you just didn't put a single thing down. You're like, okay, this is bad. Okay, so here's what happens is that you have to, if you want to, which I very much would like for you to do, is to correct the work. You get 1 point for the corrections. Very good. So your 3s can go up to 4s. Your 2s can get to 3s, right? And your 1s can get to 2s. We're good? That's the way it works. Let's see. Well, you have to tell me a sentence in English first of what went wrong. I forgot to multiply the negative or distribute the negative all the way across. That's a little sentence. Like, now I realize what it ended wrong. And then underneath it, then you do the work for it. So then you start off the problem all over again, do the work, you get the right answer. I am going to grade those again. So if you still don't get the right answer, you won't get credit for it. We're good? But if you do get the right answer this time, then it's a point towards your grade. Okay, we're good there. Cool. Real question.
How many tests are we going to have this year?
Depends how many chapters there are that we're going to cover. And let's see. No, sorry. Let me walk back that. No, I think like chapter 1 is so huge, we'll break it up into 2 different pieces. So we'll have a chapter test after 1.4, and then we'll do 5, 6, 7, 8, 9, and then have a test again. So I don't know, you roughly every 4 sections or 5 sections we do in the book. So maybe every, I imagine like every 3 weeks or so, 3 to 4 weeks we have a test. So I'll let you count that. Since we're in math class, I'll let you count. Stella. Let's see. So eventually, at the end of the game, 20% is your exam scores, 20% is your homework, 20% is something called a presentation project you guys will do in the semester, 20% is participation, and 20% is your final score. Good. Everything's brought up into 20%. Cool. Any other? Tristan. Final exam. Yeah, you guys will have a final exam on it. Okay, we're good there. Awesome.
You have a presentation at the end of the
Correct. Yeah. Towards the end, I'll talk to you guys about what presentation is, but pretty much it's anything that you connect to this class. So, last year in trigonometry class, we connected the sine waves. They're called sine waves. They connected to music. Person brought their violin. Even in class, they played it, or then they. So it's going to be like a PowerPoint presentation, but it's you connecting to something that has been taught in the class. You want to go deeper into a topic, or you connect to something you enjoy. So we had a person that does deep sea diving, and she presented how that connects to area inside trigonometry. It was just really, really cool. I learned something. That was cool. Dylan.
So when are you doing this? Is it like you're going to like bring a script, or do you have to memorize that?
It's going to be you setting up probably a PowerPoint presentation, most likely, and then going off the PowerPoint. And so you do get a presentation grade. You get a content grade as well. So we'll talk about how to best present with PowerPoint, all the little good stuff, tricks and tips of presentations. Okay, we're good there. And that's going to be after the new year, since semester ends after that. It is. It is. Okay, let's jam. 1.2 graphs. So 1.1, we went over real quick the rectangular coordinate system. We talked about Descartes and him coming up with a system that fused algebra and geometry. So now let's start graphing stuff. How do we graph stuff? That's the next question. And the basic way we graph stuff is by a table. And we'll work our way through all the different graphing stuff that we do. 1.3 you should remember. 1.3 is going to be all the formulas, the slope formulas. That'll be cool. But this is just kind of like a basic, hey, this is the basic stuff of graphing. So let's fuse algebra geometry together here. So let's go with exercise 1. So determine if 3, 2, 4, 1 is a solution to the equation. So strictly algebra here. So 3, 2, 4, 1. Oh, I forgot. Sorry. Can I change it up here? Sorry. 4, 3. That's what I wanted. So 3, 2, 4, 3. And this is just too easy one. This is not supposed to be difficult. X plus y is equal to 5. We know we can graph this. So this is a line along the graph, right? But as far as a solution is, as far as determining, making sure that something is a solution, we go back to algebra. And so in this case, this little piece right here, that's the x value, that's the y value. We plug it in, and if it makes sense for the equation, it's a solution for the equation. We're good there. So there's kind of two different ways we think about those. So let's try 3, 2. Plug it in. 3 goes in for the x, 2 goes in for the y, and if that's all good, then yes, 3, 2 is a solution. Are we good? Jump to the next one here. Plug it in 4, 3. 4 goes in for the x, 3 goes in for the y, and the question is, does that make sense? Is it true? No, it is not. And what we do is we put a legal slash through the equal sign. It's not true. We got ourselves no. All right, this is going to be the very basic graphing piece right here. You may have learned just a few little interesting stuff here, but for the most part, it's going to be very, very basic. Okay, we're good there. 1 down. So let's go the other way here. Exercise 2, graph. X plus y equals 5. All right. If you don't know what a graph looks like, if you haven't made any other tools in your repertoire of tools, you can always go back to a table. You can graph anything with a table. As long as you have points, you can connect the points together, you're good to go. So I can go like this, X, and then I make a Y table over here. Let's plug in 4 points real quickly here. So first things first is we get to pick the numbers we want to plug in. That's the cool thing about it here. And the question is, what's the easiest number to plug in? Let's see. It starts with a Z, ends in arrow. 0. All right. Yeah. Abe was already thinking 2 steps ahead. If you plug a 0 in for X, the 0 drops off, and that's exactly what we like. 0s to drop off. And we get ourselves 5 Y. Okay, again, you guys get to pick for a table. You guys get to pick what you want, plug it in, and you get out what you get from there. So another number. I don't know. What do you guys say? 1? 1 is good. Would 1 work? 1 plus y equals 5. Subtract 1, and we get ourselves y equals 4. Are we good there? 1, 4 would work. If I plug in a 2, what do you guys say will the answer there be? 3, because you can get patterns here. And hey, 3, we already know that one because we did it on the previous page. 2. All right, can you graph it real quickly here? See what the graph looks like. All right, you guys know this stuff. Is that right? This is like so. Okay, so I'm going to throw a few little interesting things at you, just for the fun of it. So the biggest number I have is 5. 1, 2, 3, 4, 5. I'm going to go out 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 0 sideways, 5 up is my first dot. 1, comma 4, 2, comma 3, and 3, comma 2. A few things. We're going to connect these guys with a straight line. Lines are always straight anyways. If you say a line, that means it's a straight line. So there's only lines and curves. Lines are going straight, curves have a little curve to it here. So I want you guys to do this here, graph this little guy, and then again, always put arrows at the end because this stuff always keeps on going and going and going. It doesn't stop. On your calculator, it stops. Is that right? But you understand it keeps on going. Just the dots run out. And then on these ones, all the graphs in your textbook here, they actually should have put graphs. They should have put arrows at the end. They just didn't. No fun. Okay. B. All right, all yours for this one. Now this one's a curve. This one, there's a little curve to it. Notice they have an x to the second power. So only little problem we have is the fact we need a lot more points because we need to figure out the curvature of it. Does it go like this? Does it go up and then comes down? We need to know. So with curves, not straight lines. Sorry. With curves, what we do is we make a lot more points here because we want to just sort of see exactly where this little thing is going to turn. Once we have enough points, then we can connect the points together. And that's exactly what your calculator does. Your calculator is kind of dumb in the fact that it just plugs in points and that's it. It doesn't do any sophisticated math to get there. All right, so off to the side, again, we're going to look for patterns as well. Anybody, what should we plug in first?
0.
0 is cool. All right, 0 plugged in. I think we can do this in our head. Is that right? 0 squared is 0. 0 minus 2 is a negative 2. All right, next one. Give me another one.
You want to just go in order if you want to skip numbers?
Whatever you like. Abe.
7.
I'm going to put a 1. Emil said 1. Abe, what do you want to say?
No, Annabelle said 1.
10. Okay. Isabel said 1.
I wanted 7.
7. Okay.
7's almost in brackets.
Okay.
Friday the 13th.
I was on Friday.
That's a little, like 3 days late. Okay, if we plug in a 1 in here, 1 times 1 is 1, 1 minus 1, 1 minus 2 is? Okay, so maybe it's not so, hold on. If we plug in a 10, 10 times 10 is 100, 100 minus 2. I don't think I want to graph that. I don't think I want to make a sheet of paper that goes all the way to 98. Okay, so we're going to rule that one out. Let's see, 7 times 7 is 49. 49 minus 2 is 40. Oh boy, I'm not sure I want to take a graph sheet of paper and do that either. So sorry guys.
I mean, you could do it. You just have to do it like alright, not technically.
That's true, yeah. Even though I do want to get a precise graph, especially where it turns. -1. Okay, I would go with that. -1 into here. -1 times 1 is -1 times -1 is 1. 1 minus 2 is a -1. Hey, that's interesting. I see the 5. 5 times 5 is 25 minus 3 by 3. That's almost like that could be okay. I'm not sure if I still want to go out to 23 because I want to get precision right here. I want to get these little small numbers very precise. -2, and then I'm going to go with +2. Just want to see what happens there. -2 times 2 is 4. 4 minus 2 is 2. +2, 2 times 2 is 4, 4, and these guys are all the same. I think I have enough. We may even want to do like 3 and -3, and if we did that, we'd get ourselves, let's see, 9 minus, that's a 7, and a 7. And we also notice this little thing right here. Okay, so let's graph this guy. So I got 7 over here. I think I'll go out 7. 1, 2, 3, 4, 5, 6, 7. 1, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so I noticed that some of you guys have just line paper, right? And then some of you guys have quadrule paper, right? It has little squares in it, right? Especially for graphing. If you can get quadrule paper, that's cool. Not required though, but if it helps. Oh, does it help? Sometimes.
Yeah, it does.
Okay.
I have some other.
Gotcha. Okay. So 0 sideways, 2 down. There's my first dot. Boom. I got 1, -1. There's my second dot. Then I go -1, -1. There's my third dot. 5. I'm going to sketch that out. -2, +2. I like this one. And then +2, +2. Okay. -3, 7. So that's going to go all the way to the top of my graph. And +3, 7. Are we good? That is a curve right there. Okay, so a few things that are happening off this curve. I got to connect them. Notice I drew my little arrow here. And also on these guys, don't make it a V shape. Make it like a squashed U shape, right? Because graphs don't go straight. This particular graph doesn't go straight. It does a corner and goes up. It actually is a smooth turn. Okay, so I noticed a few things here, guys. Let's talk about this here. So I noticed, first of all, this side is very similar to this side. Is that right? In fact, if I were to put them together like this, they would be exactly, they're fit on exactly the same thing. This is called symmetry. Okay, I'm going to figure out some tests for that symmetry here. So let's talk about that. Second of all, let's talk about, this is very important right over here, is where it hits the x-axis. We call it an X-Intercept. And where it hits the y-axis, we call it a Y-Intercept. So as far as math is concerned, those three are pretty important little pieces here. Where it crosses the axes is important, and whether it's symmetric is pretty important. And so let's do this here. How do we find the intercept here? So I want to do this here. I want to find the X-Intercepts, and I want to find the Y-Intercept. And we can do it graphically, right? Just look at a graph where we find. Like, what's the Y-Intercept? Where does it hit the Y-axis? -2. Okay. Where does it hit the X-axis? That's a toughie. Yeah, so I have 2 X-Intercepts here, huh? I have 2 X-Intercepts here. And then, but it's not, it's almost like hits like in the middle between 1 and 2, right? As we saw a graph, notice our graph is right there. It's in between 1 and 2. Because it hits 2 up here. Okay, and then the next question is this symmetric? Can you fold it on top of each other? So let's do this here. That's an algebra problem. That's a geometry problem. Let's change it up to an algebra problem to solve. We good? So here's what we're going to do. So exercise, are we on 3 or 2? You guys have to keep me up with the numbers here. 3, find X and Y intercepts. All right, and let's do the same problem that we did here, because we have the graph of it anyways here. So y is equal to x squared minus 2. So if I were to find the, let's do the y-intercept first, because that was easy here. Finding the y-intercept, all we do is we plug a 0 in for the x. So we're doing it algebraically now. We're good. Plugging in the 0 in for the x. Let's see if we get the same answer that we got before. Is that true? 0 squared is 0 minus 2 is? 2. Finding the X-intercept. What we do here is we make the y equal 0. So in this case, it becomes like this. Oh, I'm so glad we did those review of Algebra 1 stuff, because you guys totally know how to solve this one right here. What do? 2 to both sides. And I think we're going to use the square root method. Is that right? Because we have something that's a perfect square over here. Perfect. Yep, we're going to put like this. And then on the side that we're going to keep, not the side we're going to cancel, the side we're going to keep, we're going to put plus or minus. So we get ourselves plus or minus root 2 is equal to x. Perfecto. Okay, here's what we got. Let's go back over here. So the way we label this, the way we find the answer is we go like this. We just label it as 0, negative 2. By labeling it, the 0 tells me what intercept I'm using, and the other side tells me what the answer is. So for this one, I got the y-intercept is 0, negative 2. The x-intercept is, and let's see the way your book likes to write it here. I think it writes it separate, yeah. The book likes to write each of them separate. So positive square root 2, 0, negative square root 2, 0. Boom, are we good there? And we'll talk about symmetry in just a second here, and then we'll jump to some other stuff here. Okay, B, all yours for B. Tell me if you guys are ready. All yours, from beginning to end. Can you find for me the x and y-intercept of this little guy here? Challenge for Owen. Here it is. Cool. All right, let's go with it here. So going and finding the y-intercept, since that's the easiest, we're going to plug in a 0 for the x. And if we do that, we get ourselves a 0. Okay, so I got 0, 0. Very okay there with the y-intercept. We'll jump into x-intercept. And make the y be the 0 value now. And we got ourselves a little bit ahead of us. What did you do? For y? This one, for the x.
Well, I divide by both x out of that, it becomes x times x squared minus 4. And then you can just divide by x and give it the x.
Oh, no. Can't divide by x.
That's how I did it. And when I plugged what I got for x.
Got it, yeah. So let's go with it here. So this one, if you're trying to solve for things here, because x could actually be a 0, right? Whenever in mathematics, we can't divide by zeros, right? So as long as you're sure for sure that you can't, that x is not a 0, you can divide by it. Here we're not sure. So we're going to keep on factoring. So this guy factors into x plus 2, x minus 2. Good there? Hey, that's what we did in the appendix. I remember that. I remember solving for this. So then so there's 3 things multiplying each other. Each of them is going to be set equal to 0. So x is equal to 0, x plus 2 equals 0, x minus 2 equals 0, and solve each of those. This guy's solved already. Done. This one needs to have a subtract 2 on the end. That's done. This needs to add 2, and that's done. So I got my answers of 0, 0 here. A y of 0 gives me x of 0. A y of 0 gives me negative 2 of x. And a y of 0 gives me a positive 2 of 0. Now, Owen, it worked for you. It worked just fine because notice these guys are the same, right? So in that case, it worked. So the final list that I have, all the intercepts are 0, 0, negative 2, 0, and positive Are we good there? Oh, yes, let's go. Let's see what the line is. That's perfect, Dave. Thank you. I got a hit here. I got a hit here and a hit here. And Dave is asking which way does the line go? Absolutely. That is perfect. It goes up like this. If I doesn't turn this way, it's the zero again. It goes, uh-oh, wrong way. Let's go this way. And there's your 3 zeros. That is awesome. Okay, talk to me. Is that symmetric? If I were to fold this thing along the y-axis. Yeah. Hold on. If I were to fold it along the x-axis, will that work? Okay. The fun part. You guys ready for this one? If I were to fold it along the x-axis and then also along the y-axis, would that? Whoa! Let's check this out. Let's see. Let's see if this makes sense. If I were to fold it along the, let's flip along the x-axis. Let's go like this right here. Everybody agree there? That's gonna go like this. Flip it along this guy. Just turn it like this. Go like that. Right? And then we're gonna flip it along the y-axis. So we're gonna flip it along this guy. And if I do that, will that do it? So just kind of in your mind, kind of just do this. Just kind of flip it around this way. So this guy's gonna go. Oh, does that look like the original one? Okay, so we have 3 different, we call them symmetries on our hands. We have the x-axis symmetry, we flip it around the x-axis. We have the y-axis symmetry, flip it along here. And then we have something called flipping around the origin. Origin is actually kind of like the x and the y together at the same time. Let's see. So we technically don't say it's a spin, even though, yeah, you could think about it. Let's see. Yeah, you can think of it as a spin as well. Half turn spin. Oh, and that is cool. Okay, so symmetry. Let's go with it here. We have 3 of them. I should say symmetry. Sorry, symmetry, because that's the concept. Symmetry is a concept. We have 3 different kinds. We have the x-axis, or let's go in order here. Y-axis, what we did? Oh no, we did x-axis first, right? X-axis symmetry. X-axis symmetry, it says this. If I take a positive x, positive y, it's the same thing as having a positive x, negative y. Notice the other value, and other variable that's changing. And let's go back in our mind and see if this makes sense. Notice when we flip along the x-axis right here, right? Notice all the positive y values became negative y values. Are we good? So think about this. Stuff on top becomes stuff on bottom. Okay? Y-axis symmetry. A positive x, positive y, and that should be a y, sorry guys. Y becomes negative x, positive y. And symmetry about the origin. It means I'm going to spin it both ways here. So I'm going to go positive x, positive y could be changed into a negative x, negative y. Okay, so we got one of 2 things here. We could look at a graph, right? We could say, oh, can I flip it upside down? Yeah, that looks about right. Right? And then can I spin it this way? That looks about right. Okay, then, but whenever we look at graphs and do that, we kind of not for sure, right? But once you plug in numbers, then you know for sure. So this is what we want to do. So exercise what again? Help me out. 4. Okay. Is that a guess by Abe? That's a guess by Abe.
We just did
3. Okay. Good guess by Abe. All right. Fine. So let's work on the ones that we just did. Let's work on this one here. So testing for symmetry. Test for symmetry. And I'm trying to make the lecture so that it just kind of flows. We just move from one problem to another so that it kind of makes sense as we go through it. So the previous problem that we had, test for symmetry here. So y is equal to x cubed minus 4x. One that we just did. By the graph, when we flipped it, it didn't have any x-axis symmetry, right? And we flipped along the y, we didn't have the y, but we did have the origin, is that right? Well, we did both of them. So let's see. How do we test it? We do this. We plug in, we're gonna plug in a negative for the y value. And if we get back to what we had before, that means it doesn't matter which one we plug in. A positive y or a negative y, it wouldn't matter. Does that make sense? Like this one or this one, it would matter because we have x-axis symmetry. So if I were to plug in a negative for the y value, the question is this: can I get back to my original function? And the reason why I say get back to the original function is we just solve for y. We solve for y and we see if we get the same function back again. So I'm going to multiply through by negative 1 here. And I get myself negative x cubed plus 4x. So the question is that the original function? No, that is not the original function. Next, we go over here. We test for the y-axis symmetry. So in this case, we're going to plug a negative for the x value. So it's y is equal to negative x to the third power minus 4 times negative x. So we plug in negative x. And the whole hope is this right here. If I plug in a negative on this side of my y-axis, right, it's going to do the same thing that it does on this side. That's what it's saying. Graph-wise, what I'm trying to figure out is this. If I have a dot over here, and the negative x, positive y, I'm also going to have a dot over here in the positive x, positive y. I'm going to see if those dots are there. Those dots are the same. All right, let's check it out. Negative x times negative x times negative x. Negative x to the third, perfect. And then negative 4 times negative x, positive 4, is that right? X. All right, in order for it to look like the original one, I think I'm going to factor out a negative. Or does it look like the original one? I guess maybe we can just stop there. No, it doesn't. So no on this one. Let's go over here. So origin. If I start something in quadrant 3, it's going to be the same thing that I see in quadrant 1. And vice versa. If it starts in quadrant 4, same thing as quadrant 2. That's kind of the flip of things. So I'm going to put in a negative y, and I'm going to put in a negative x. And I'm going to see if those guys give me the exact same problem all over again. So changing the x, changing the y's to negatives gives me the exact same problem with the positive. So negative y on this side, that's cool. Negative x times negative x times negative x is negative x cubed. And negative 4 times negative x is a positive 4. Everybody agreed there. I like it solved for y, so I'm going to multiply through by negative 1. So negative 1 on this side, negative 1 here, and those will cancel. Negative 1 times that will give me a positive. Negative 1 times that will give me a negative. And do I get back to my original function? Yes, it does. Okay, so that anything that I see in quadrant 3 will be reflected in quadrant 1. Anything I see in quadrant, so we're going to go this way, in 2 will be reflected in quadrant 4. That's what I just figured out. Cool, this is a yes. So we have symmetry about the origin is super cool. Okay, are we good there? Symmetry is all taken care of, done. Next, the fun part is sometimes what we can do is we can graph using these guys. We'll stop there. Let's see. We can graph. It's a little bit of a help there. That's what symmetries are for. And then it allows you to do a few computational stuff with them. All right, last part that we want to move into is the circle. Last part of dealing with things is the circles. I guess we'll deal with a lot of them here. Boom. You guys covered circles in geometry, I assume. Maybe. You guys covered circles, and then you guys just did the compass, right? You guys drew circles, a compass, and all the good stuff here, right? Did you guys? Yeah, we don't do too much in geometry with circles, no. And so this comes in as saying this right here. So let's do this here, circles. So if I have a circle here, let's look at the algebra of circles, because this is algebra class. So I have a circle at the origin. And remember the Pythagorean theorem? Remember Pythagorean theorem says, if I have dot here in space, we did distance formula. Didn't we do distance formula already in the class? So what is the distance from here to here? If this was, let me do it another way here. Let's see. If this was X and Y from the origin, and this guy was R. Everybody okay with the relationship here? That would be a relationship based upon Pythagorean theorem, because he's a super cool guy. It would have been x squared plus y squared is equal to r squared. Are we good? Well, that's exactly what a circle is. It's just all the different points that you can think of, right, that fulfill that criteria. And so the formula for a circle, this one is at the origin. What we want to get to is we want to move that little center right here. The center is at 0, 0 right now. We want to move that center, we want to move it away from the origin. So this is the cool stuff. And so now we have a circle. I could put a quadrant 4 or 3 or 2 or 1. It doesn't matter, right? But I've moved so that the center is right here. And I still have this. I still have it going. Isn't it still R away from things? Is that right? But now this guy is, I'm going to call it H comma K. That's what I normally would do. All right, so now the question is, how does this formula change? Any guesses on the formula changing? I think I still have R squared in there, right? But instead of being at 0, 0, now you've moved it out this way here. So formula goes like this. It's going to be x minus h squared y minus k squared is equal to r squared. And there's my little formula for a circle that's not in the origin. Now I can put the circle anywhere I like along the Cartesian coordinate. H. And H is the center. So center is at H comma K, and the radius is R. Are we good? Center is at HK. That is so cool. So now we have a circle I can float anywhere I like along my little coordinate plane. Now let's see, we're in algebra 2. When we get to trigonometry, literally we look at a unit circle again and we see some little relationship there, and we start a whole new branch of mathematics because we see a little something right there. And Pythagorean theorem comes into it, but this right here is the next class here. And trigonometry is just seeing that and seeing it like, hey, I wonder if. That's it. I wonder if. And then a whole new branch of mathematics developed. Okay, guys, let's go with it here. So we want to develop this whole concept of, or practice with this here. Exercise 5, I assume. Tell me if I'm true. So I have a point. A point. 3, 4 is on a circle with a center of -1, 2. Of a circle. So I know a point, it's called 3, 4. I know it's on the circle, which means it's on the outside of the circle. I know the center of the circle is at negative 2, 3. So the question is, can I write the equation of that circle? So
Find R.
as in, find R probably. So let me draw it out. Let's see like a visual illustration here. So 3, 1, 2, 3. 1, 2, 3, 4. So 4 is right over here. That's a point that's along the circle. Negative 1, comma 2. So this little point right here, that is the center of the circle. So center. So if I were to take that center, think of it as a compass, right? And I would just make my little circle. The circle kind of looks like this. Tell me, agreed? Is that about right? Kind of, sort of. So I want the equation of that circle right there. Because I knew the center, at least. I knew the center was right here. I knew this was a point on it, so it's almost like a visual compass in my mind.
You only need 1 point.
Oh, so really interesting. So with as long as you get a precise point for circles, you just need 2 points for a circle, right? That and that. And then we go.
Oh, yeah. Yeah.
Now, interesting thing is, if you don't know the center of a circle, so like this, Abe, if you just had this one, this point and this point is on a circle, then you have so many different circles, right? Right. But once you know the center and another point, you're good to go. Okay, let's jam. So I'm thinking I'm going to use the formula for the circle, right? Because that's the whole point. Formula for the circle is h minus k, is this y minus k squared is equal to r squared. So y and x are variables for me. H and k I already know. So really, as Owen said, it's just about finding r. That's the only point here. So you could use Pythagorean theorem if you like, but really you can plug the values in. So let's say this guy's going to come in as a 3. This guy's going to come in as -1. Are we good there with -1? Because that's the h value. This comes in as a 4. This comes in as a 2. And we're trying to find r. So kind of careful when you put this in. This comes in as a -1 squared. This is 4 minus 2 squared and r squared. Okay, everybody okay with plugging in those values there? So you know what the x values are, because that's on this circle. You know what the h and k values are, because we know the center. So let's see, this becomes plus plus. This becomes plus plus right here. And I get myself a 4 here. I get myself a 2 here. I get myself a 16 plus 4. That's a 20. And take a square root of both sides. And how come I'm not putting plus and minus? Why am I not putting plus and minus?
Because it makes sense that the circle has negative distance.
Perfect, yeah. Remember, you can't have negative distance. So you have positive distance is always positive, so we don't need the little plus sign. I think we're good, guys. Look at this. X minus h, which is -1, right? So everybody okay with the +1? Can I put a +1 there already? Y minus 2 is equal to, actually no, hold on. Sorry guys, didn't even need to do that right here. I could have just put 20, right? Because my formula is in terms of r squared already, right? Sorry, I just need to get down to this right here. So, sorry, back up just a little bit here. That's what I needed for my formula. I don't need to solve for r, I just need to get to r squared.
If it was root 20, wouldn't that be 2 root 5?
2 root 5, yeah. If we need to know the exact, so the question is find the radius of the circle. The exact value of radius of the circle is 2 root 5. Okay. Are we good there with lecture? Let's stop there. I'm going to hand back your exams real quickly here, and then we'll go from there. So, just real quick here. So you can hand corrections of your exam. 4 points is perfect square. Perfect score 3 is you missed a little something. 2 is you missed quite a bit of something. Minus 1 was you missed a lot of something. And 0, you did not put anything down. You were just off. We're good? So a sentence in English that says what you did wrong. And bring those corrections. So this is Monday. How about this? Bring corrections by Friday. We good? And I'll